Okay, we've already seen that the choice of coordinates is very important if we want to succeed solving problems in classical mechanics. Let's now go back to our old friend the pendulum and write its equations of motion. In a previous video we discussed briefly the pendulum. The pendulum was assumed to have a point mass oscillating attached to a rigid bar that can oscillate or rotate. We assume that the rigid bar is massless. We also assume there is no friction between the bar and the fulcrum. This pendulum, depending on the energy, can oscillate back and forth, or it can just oscillate, moving in circles. When we talked about it previously, we mentioned about the two forces involved, the gravitational force on the bob and the tension from the bar. This is nicely represented in a free body diagram. If we assume everything is perfect, beautiful, without perturbations, the motion will be in a plane. So this simplifies things. If we hadn't studied polar coordinates, we would attack this problem from Cartesian coordinates. Let's assume so. Let's try to solve it using Cartesian coordinates. We choose the center of coordinates to be at the fulcrum, always distance L to the bob, and horizontal and vertical axis. We need to write Newton's second law in the horizontal and the vertical axis. The force of gravity is always vertical, but the tension is not. Tension depends on where the bob is and points at an angle theta. Newton's second law in both axes are In these two equations we have three unknowns though, x as a function of time, y as a function of time, but also the tension, which also depends on time, or better, in the position. Because of the constraint of this motion, we know that the distance from the bob to the center of the coordinate system will always be L. So x squared plus y squared is equal to L squared. We can eliminate tension T from the first two equations. And use the constraint equation to write one equation in terms of, let's say, x. We write that s is the square root of L squared minus y squared. We derive x twice. And we substitute into the first equation. After some wibbly-wobbly math stuff, this not so nice equation here is the differential equation of motion of the pendulum in Cartesian coordinates. Now, you impose the initial conditions and find a way to integrate this beast. Well, I don't even see the back and forth motion in this equation, or the loop motion. I don't come up with a clear, easy solution to this. We could integrate it numerically though, but probably the smart thing to do is to use polar coordinates instead. In polar coordinates x and y are written as r cosine and r sine of the angle theta. In order to write Newton's law, we need to think of the forces we have here. These forces are the tension and the weight, but we need to write them in polar coordinates. Tension is always radial, that one's easy. Force of gravity has a radial component and a tangential component. The radial component is mg cosine of theta, while the tangential component is minus mg sine of theta. In a previous section of this chapter 1, we found the acceleration in polar coordinates. So now we have the forces in polar coordinates and the acceleration in polar coordinates. We can now write Newton's second law in polar coordinates for this particular problem. Which we can separate into radial and tangential. We know that motion is in the theta direction. There's no motion in the radial direction. So, which after a bit of wibbly-wobbly mathy stuff, we get that theta to dots is minus g over L sine of theta. This looks like a nicer differential equation, but there's no analytical solution either. We have to solve this equation numerically. But in any case, this differential equation already contains information we can extract. The angular acceleration opposes, with a minus sign, the displacement of the mass from the equilibrium position at theta 0. This is a restoring force that points the bob back to 0. This is going to give the back and forth motion. If we use the second equation, the one in the radial direction, we can get the expression for the tension, which it is easy to see that tension has two ingredients, one from the projection of the weight and the other from the centrifugal force of the rotational motion. Remember that by choosing polar coordinates, we're not in an inertial frame anymore, and there can be fictitious forces caused by this choice of coordinates. So, choice of coordinates is really important. This removes most of the factors that are not really relevant for the problem. For example, the motion in the r direction. We'll come back to this point later in the course. Now, may the science be with you.